Okay, in this video I'm continuing my discussion of laser diode basics, and I just got done explaining about laser diode operation and the laser modes that result from the combination of the gain profile and the longitudinal modes of the cavity. Okay. Yeah, these are called longitudinal modes. How do we do this in a real semiconductor device? Well, what we do is we take a chunk of semiconductor, okay, and at the very basic, we polish the end faces, and make them into mirrors. We may make them with thin film, multiple thin film layers to make very high quality mirrors that work at a certain wavelength, but let's just take that they're polished, okay? And so our resonant cavity is going to be in this direction, L, okay? Now what we need to do is we need to somehow get our active gain medium here, and what we're going to do is we're going to have a multi-layer stack, and in this multi-layer stack we're going to have our active layer, but we're going to surround it by layers with higher refractive index, which are called confinement layers. And in fact, what we do is we get ourselves an optical waveguide, very much like the slab waveguide we studied in Chapter 4. So we have higher index on the outside, and so we have total internal reflection in this layer here. Okay. Now we put electrodes on the top and the bottom, one way somehow, and we confine those electrodes to some horizontal, so we confine it so that the electrodes can confine the light to the part of the active layer which is actually going to be active is confined laterally. Okay, so we have confinement in the vertical direction here due to the waveguide, the confinement layers. We have a cavity back and forth, and then we have confinement in this horizontal direction due to the shape of the electrodes. Okay, and so it's this region here that will emit the light. Okay, and that's basically how laser diodes are constructed. In fact, without the mirrors, we have the same basic construction for LEDs. Okay. There's an important difference between lasers and LEDs, and I'll draw the two cases here quickly. Okay, for the case of a laser, well, let's do the case of an LED. We have this as our active region. We have our confinement layer in the vertical direction. We have this is our active region, and for the LED we have a very small dimension in one direction and a much larger dimension in the other, and this light cone that comes out of here will be shaped like this in the LED case. It'll be much wider in the direction where we have a much wider dimension. Okay, so this is what the output cone of the LED will look like. The laser, it turns out, is just the opposite. And it's just the opposite due to diffraction. Remember that the laser light is coherent, and so it diffracts. And let me go ahead and draw my active region, my confined waveguide, and then draw my waveguide region here. And it behaves in just the opposite way, because a small slit in a diffraction grating will cause a wider diffracted beam, and so the laser output will be just the opposite. It will be wider in the direction of the smaller dimension and narrower in the dimension of the larger one. Okay, kind of interesting how that works, I think. There's my picture, and this is a diffraction effect. Okay. What I'll also do in this video is give you an overview then. As I say, both lasers and LEDs are essentially constructed this way, with an active layer sandwiched between confinement layers with higher index. Okay, and that gives us an optical waveguide, slab waveguide, that we've studied so much. And I'll also give you then here a quick overview of, the other thing I wanted to say here was that this type of structure, where we have multiple layers, of semiconductor, are called double heterojunctions. Okay, so the PN is a single heterojunction, and when we have these multiple layers, they're called double or multiple heterojunction layers. Okay, I guess I'll stop here on this video, and we'll do the material systems in the next video. Thanks.